Assalamu alaikum. In the name of Allah, who is the most beneficent and most merciful. Today I am going to present the topic complexometry. First, let me introduce myself. My name is Arif Fatma from Department of Base Chemistry. My ID is 001 and this is the presentation of analytical chemistry which is submitted to Sir Hazer. So here is the introduction. What is complexometry? Complexometry is a volumetric analytical method which is based on titration of metal ion solutions with a substance that combined with metal ions and yields complex compounds, for example, ADTA. ADTA is a ethylene diamine tetraacetic acid. So many metal ions form slightly dissociated complexes with various ligands, which is called complexing agents. The analytical chemists make judicious use of complexes to mask undesired reactions. The formation of complexes can here the masking agents is a reagent that protects some component of the analyte from reaction with EDTA. Masking used to prevent one element from interfering in the analysis of another element. So, the formation of complexes can also serve as the basis of accurate and convenient titrations for metal ions, in which the titrant is a complexing agent. So, what is titrant? Titrant is a substance that is added in the titration. Complexometric titrations are useful for determining a large number of metals. Selectivity can be achieved by appropriate use of masking agents. Other complexing agents that react with interfering metal ions but not with the metal of interest. And by pH control, since most complexing agents are weak acids or weak bases whose equilibria are influenced by pH. The EDTA titration of calcium and magnesium is commonly used to determine water hardness. In the food industry, calcium is determined in cornflakes, and in the plating industry, nickel is determined in plating solutions by complexometric titrations. In the metal industry, in etching solutions, and in the pharmaceutical industry, aluminium hydroxide in liquid antacids is determined by similar titrations. Near all metals can be accurately determined by complexometric titration. The complexing reactions are useful for gravimetry, spectrophotometry, and fluorometry, and for masking interfering ions. So, what is complexes and formation constants? How complexes are stable? Complexes play important roles in many chemical and biochemical processes. For example, the heme molecule in blood holds iron tightly because the nitrogen atom of heme forms strong ligating or complexing bonds. In general, the nitrogen atom derived from an amino group is a good donor atom or complex. The iron, as the form of iron 2, in turn bonds readily with oxygen to transport oxygen gas from the lungs to elsewhere in body and then easily releases it because oxygen is a poor donor atom. Carbon monoxide kills because it is a strong complex and displaces oxygen. It binds to heme 200 times more strongly than does oxygen and forming carboxyhemoglobin. Many cations will form complexes in solutions with a variety of substances that have a pair of unshared electrons, for example, nitrogen, oxygen, sulfur atoms in the molecule, which are capable of satisfying the coordination number of metal cation. So, what are coordination number? The number of atoms or ions which are immediately surrounding a central atom in a complex or a crystal is called coordination number. So, what is ligand? The metal cation is a Lewis acid electron pair acceptor, and the complex is a Lewis base, which is electron pair donor. The number of molecules of complexing agent called the ligand will depend on the coordination number of metal cation and on the number of complexing groups on ligand molecule. Most ligands contain oxygen, sulfur, and nitrogen as the complexing atoms. Ammonia is a simple complexing agent with one pair of unshared electrons that will complex copper ion. Here is nitrogen is a complexing agent in this molecule. The copper ion acts as a Lewis acid and the ammonia is a Lewis base. The copper hydrated ion is pale blue in solution while the ammonia amine complex is blue, day blue. A similar reaction occurs with green hydrated nickel ion to form a day blue amine complex. So, what is formation constant? Ammonia will also complex with silver ion to form a colorless complex. Two ammonia molecules complex with each silver ion in a stepwise fashion, and we can write an equilibrium constant for each step, which is called the formation constant, and it is represented by Kf. Here is the reaction in which silver reacts with ammonia and forms silver ammonium ions. Here, the first formation constant is 2.5 into 10 raised power 3, and the formula for this formation constant is equal to number of concentration of product by concentration of reactant. In the second step, silver ammonium ion react with ammonia and forms silver diamine, and in this reaction the formation constant is 1.0 into 10 raised power 4, and here's the formula is equal to formation constant is equal to concentration of product by concentration of reactant. The overall reaction is the sum of two steps, and the overall formation constant is the product of stepwise formation constants. Here in this is the overall reaction of the previous two stepwise reactions. In this, silver reacts with two ammonium molecules and forms silver diamine, and here the formation constant of both overall reaction is 2.5 into 10 raised power 7. So what is dissociation constant? We could write the equilibria in opposite direction as dissociation. If we do this, the concentration terms are inverted in equilibrium constant expressions. The equilibrium constant then are simply the reciprocal of the formation constant, and they are called instability constant or dissociation constant. And it is represented by Ki and also Kd. In case of instability constant, it is represented as Ki, and in case of dissociation constant, it is represented as Kd. Here is the reaction in which silver diamine react uh, in reversible reaction. It converts into silver ions and two ammonia molecules. And here the dissociation constant is equal to reciprocal of formation constant, and in this case the formula is opposite of formation constant, which is equal to concentration of reactant by concentration of product by concentration of reactant. So the overall dissociation constant for this reaction is 4.0 into 10 raised per minus 8. You can use either constant in calculation as long as you use it with the proper reaction and correct expression. You will note that the dissociation of an acid is um, HA is equal to H plus A minus is in fact very simply to the dissociation of a metal ligand complex in which metal ligand is equal to metal plus ligand. However, the convention is to write the first as a dissociation reaction and the second as an association reaction. Here HA is equal to H plus plus A minus is the dissociation reaction, and in the second is metal ligand is equal to metal plus ligand is the association reaction. So what are chelates and EDTA, the ultimate titrating agent? So what are chelates? The term chelate is derived from the Greek term which is meaning and claw-like. Chelating agents literally wrap themselves around a metal ion. Simple complexing agents, for example, ammonia, are rarely used as titrating agents because a sharp endpoint corresponding to a stoichiometric complex is generally difficult to achieve. So, this is because the stepwise formation constants are frequently close together and are not very large, and a single stoichiometric complex cannot be observed in this reaction. So, the certain complexing agents that have two or more complexing groups on the molecule, for example, nitrogen, sulfur, oxygen, however, do form well defined complexes and can be used as titrating agents. Schwarzman demonstrated that a remarkable increase in stability is achieved if a bidentate ligand is used. Bidentate ligand is in which one with two complexing groups attached. For example, he showed replacing ammonia with the bidentate ethylene diamine. This results in a highly stable complex. The most generally useful titrating agents are amino carboxylic acids, in which the amino nitrogen and carboxylate groups serve as ligands. The amino nitrogen are more basic and are protonated and is more strongly than the carboxylate groups. When these groups bind to metal atoms, they lose their protons. The metal complexes formed with these multidentate complexing jets. Multidentate complexing jets means in this uh, different more types of complexing groups are attached, or often 1:1 regardless of the charge on metal ion, because there are sufficient complexing groups on one molecule to satisfy all the coordination sites of metal ion. So these are some terms. What is chelating agents? An organic agent that has two or more groups and which is capable of complexing with metal ion is called a chelating agent. The second term is chelates. What are chelates and ligands? The complex formed in the reaction of chelating titrations is called chelate, and the chelating agent which is used in complexometry titrations is called ligand. What are kilometric titrations? Titration with a chelating agent is called a kilometric titrations, and complexometric titrations is also called kilometric titration, and it is the most important and practical type of complexometric titrations. So, what is ethylene diamine tetraacetic acid? The most widely used chelating agent in titration is ethylene diamine tetraacetic acid. The formula for EDTA is follows. The below formula is for EDTA. In this, each of the two nitrogen and each of the four carboxyl groups contains a pair of unshared electrons, which is capable of complexing with metal ion. So EDTA contains six complexing groups. Um, four are carboxyl groups, and the two are nitrogen groups. We will represent EDTA by symbol H4A. It is a tetraprotic acid, and the hydrogen in uh, EDTA refer to four ionizable hydrogen belonging to four carboxylic acid groups. At sufficiently low pH, the nitrogen can also be protonated, and this diprotonated EDTA can be considered as hexaprotic acid. However, this occurs at a very low pH, and EDTA is almost never used under such conditions. It is unprotonated ligand Y4- that forms complexes with metal ions That is, the protons are displaced by metal ion upon complexation. So, what is the Chilon effect? Multidentate chelating agents form stronger complexes with metal ions than those similar bidentate or monodentate ligands. This is the result of thermodynamic effects in complex formation. Chemical reactions are driven by decrease in enthalpy and by increasing entropy. The enthalpy change for ligands with similar groups is often similar. For example, four ammonia molecules complex to copper and four amino groups form two ethylene diamine molecules complex to copper will result in both the same release of heat. A chemical process is spontaneous when the free energy change. However, more disorder or entropy is created by dissociation of copper complex in which five species are formed than in the dissociation of copper complex in which three species are formed. Thus, multidentate complexes are more stable and have larger Kf values. Kf means formation constant values because of the entropy effect. So, this is known as the Kilon effect or chelate effect. It is pronounced for chelating agents such as ethylene diamine tetraacetic acid, which have sufficient ligand atoms to occupy up to six coordination sites on metal ions. So here is the EDTA equilibria. We can represent EDTA as having four Ka values corresponding to the stepwise dissociation of the four protons. In the first step, one hydrogen is protonated, and here's the formation constant. Here is the dissociation constant is 1.0 into 10 raised by minus 2, and in the second step two protons are protonated, and the formation dissociation constant in this reaction is 2.2 into 10 raised by minus 3, and the third step third proton is protonated, so the K value for this reaction is 6.9 into 10 raised by minus 7, and the in the fourth step fourth proton is protonated, and the Ka value for this reaction is 5.5 into 10 raised by minus 11. So here is the formation constant for calcium. Consider the formation of ADTA chelate of calcium. This can be represented by calcium plus by 4 minus, and it forms Ca2 minus, and this is the reversible reaction. The formation constant for this reversible reaction is the equal to concentration of product by concentration of reactant. That's all from my side. Thank you.